Hello Hopewell, this is Mr. Steinberg, and before we begin our lesson, I just wanted to take you through a little bit of a warm-up. The distance between 2 points. How do we find and determine the distance between 2 points is what we're going to start in Chapter 8. If I have 2 points, and they share the same y-coordinate as negative 9, 6, and 7, 6, 2, then what do we know? We know that these 2 points are on the same horizontal line. And if I sketched a picture, negative 9, 6 would be somewhere here in the second quadrant, positive 7, 6 would be somewhere in the first quadrant, then I would merely just count 9 boxes till I get to the y-axis and 7 more boxes, and horizontally, these are 16 units apart. How do I know this? Because a horizontal distance, you could just count boxes. Likewise, for this next exercise, 7, 2 and 7, 6, what's their distance apart from each other? So 7, 2 to 7, 6. If I do another sketch, 7, 2 and 7, 6, we notice they have the same x-coordinates in common. So the distance between 7, 2 and 7, 6, all we need to do is count the difference of the y-coordinates. From 2 to 6, that means that this has a distance of 4 units. All right, now here's the real question. What if I take these 2 points? What if I wanted to find the distance between 2 points that are not on the same horizontal or vertical line? Well, if I want to find the distance between negative 9, 6 and 7, 2, what I can do is imagine a line segment connecting them, but then also break it down into what I did in this previous 2 exercises. The previous 2 exercises, I took the distance between negative 9, 6 and 7, 6. Negative 9, 6 and 7, 6. And I found that that was 16 units horizontal. And I found the distance between 7, 2 and 7, 6, which is a distance vertical. So any diagonal distance can be broken into its components of horizontal and vertical. We said that the horizontal distance was 16 and the vertical is 4. What shape do I now have? I now have a right triangle. And in order to use and find the hypotenuse of a right triangle, we would use our Pythagorean Theorem. Our a squared and b squared, the length of our legs, equals the hypotenuse squared. So 16 plus 256 equals c squared. If I add these together, then I would get 272. And when I square root 272, I'd like to simplify this answer as a distance. What I did notice is 256 is 16 squared, and there's another factor of 16. So I have 16 16s here. One factor of 16 there, that's 7 16s. So I know that this breaks up into these 2 radicals. So the square root of 16 times the square root of 17 equals the square root of 272. So our final value for c, the distance between these 2 points, would be 4 root 17 units. All right, after watching this exercise, now I get to explain what we're beginning Chapter 8 with. We're beginning with something called the distance formula, and it's something that you should be familiar with. Since this is a new chapter, I'd like to give you a little bit of a background. This chapter deals with conic sections. How many different ways precisely can we slice 1 or 2 connected cones together, and what are the resulting shapes of them? More on that later. In our first section, we're going to use the distance formula to find the distance between 2 points that are not located horizontally or diagonally, not horizontally or vertically away from each other. In our first exercise, what we can tell is we have 2 points, neither their x-coordinates nor their y-coordinates match, so they are located on some sort of diagonal. What the formula says we need to do to find the distance between any 2 points, x1, y1, and x2, y2, can be found by taking the square root of the difference of x2 minus x1 squared plus the difference of y2 minus y1 squared. But what does this all mean? Think back to our previous exercise. If I take the 2 x-coordinates and subtract them, I find the difference for them. That's just like in our warm-up, finding the horizontal distance between these 2 points. So a change in the x means what is the difference of the x-coordinates. That became one of the legs of our right triangle that we used to find our diagonal distance. That became one of these legs, the horizontal legs. The change in the y-coordinates, squared, would be the vertical leg in a right triangle. Now, why am I squaring those two sides? Because when you use the Pythagorean theorem, we square the horizontal leg and the vertical leg. What do we do to solve for C in that last exercise? Didn't we have to square root from this step to that step? So we have a square root. This distance formula is exactly the Pythagorean theorem, just written as coordinate pairs. So what I'm going to do is I'm going to begin by doing our first exercise. I may never label these points ever again, but I'll label them the first time we do it. Here's x1, y1, and x2, y2. The value of our distance can be found by taking the second y coordinate, the second x coordinate, subtracting the first x coordinate, and squaring that. It's taking the difference of the x's. That gives you the horizontal leg. Then taking the two y coordinates, finding their difference, and squaring them. Adding the squares of these differences of the y's and the x's will give us the sum that equals the hypotenuse squared. Because it's a distance, I want to square root this. So let's simplify all this. According to order of operations, I'm going to subtract. I get 4, and 4 squared makes 16. Plus 2 take away 5 is -3, and -3 squared is 9. The square root of 25 means these 2 points are exactly 5 units away from each other. Moving on to questions 2 and 3. I may not label these, but I will show you the work. The distance between these two sets of points, 10 minus -5, would be 15. 7 minus 22 would be -15. So I'm still doing the change in the x and the change in the y. Now I'm going to square each of these because these represent legs of right triangles. I have 225 plus 225, which gives us 450. So our distance is the square root of 450. We always need to simplify our radicals. What is the largest perfect square that goes into 450? Well, both of these are like terms, like 225 and 225, and both of these are the squares of 15. So I think 225 is the largest perfect square that goes into 450, and I think it goes in twice. Our simplified yet exact distance would be 15 root 2 units. That these points in question number 2 are 15 root 2 units away from each other. Concluding with this third example, the change in the x from -12 to 11 is 23 units. Plus the change in the y from +1 to -25 is -26 units. When I square each of these, let's see, I know 26 squared is 676. And let's see, 23 squared, I somehow don't remember that one, so I'll use my calculator, is 529. Add these both together, I get 1,205. Let's see, 1,190 plus another 15. Good. What I'm going to next try to do is simplify this radical. I know 5 will go in because it ends in a 5. 5, 6, 7, 8. Okay, it does not divide by 3. I think 5 will go in something like 241 times. But 241 is prime, and so is 5. So nothing simplifies. So the best I can do is leave it as the exact radical, and it is in its simplest form to begin with. So these are the lengths of line segments in between two endpoints, or the distance that two endpoints are away from each other. I'm going to stop the video and move on to our next one.